Alright, on to the final problem of our DGD. So this problem is 3.54. A rectangular gate of a width of 2 meters is hinged as shown. And what we're looking for is this tank will fill up with water. And we're looking for, at a certain height, h, this hinge will tip over, and we're looking for this that height h. So to do that, first thing we'll notice is that this problem is a force balance problem, where what we're looking for is there's going to be a resultant force created by the water pressure on this top face of the door right here. So this will be F1, and then there will also be a resultant force created by the water pressure F2 at the bottom right there. And what we're looking for is when will the force F1 be greater than the force F2, but it's not necessarily the force, it is the moment about the hinge that we're looking for. So this can be expressed obviously as a sum of moments to 0, but also in an integral form, where we have the integral over the area 1. So the area 1 is going to be this section right here, times the certain distance y, p1 d a1 is going to be equal to integral of the surface area a2 y p2 d a2. So now if we look at this equation is essentially the sum of the moments is equal to 0. What we have right here is a pressure times an area, which is a force, times the distance. What we want both of these to be equal, which will be the balance point, which means that if we increase the height h, we will tip over this balance point. So these integrals can be expanded in the form where we have, so this is an area, so this can be also written as 0 to the width, 0 to, so L1, I will define L1 here as being 0.55 meters, and L2 being equal to 0.45 meters. So the integral L1 y p1, and this is now dA is going to be dy dz is going to be equal to, well, the same thing, integral 0 to the width, so this is our depth, 0 L2 y p2 dy dz. All right, so now the first thing is P1. Well, what is P1? So that is, we'll write this down again, W 1 is y, so P1 is rho g. Now h, well, this h right here, we're just going to write this down as h1 for the time being, but you'll notice that as we change this, because we're taking an integral, this h is going to depend on whatever value y is taken. So we know that h1 right here is going to be a function of y, and then this is also dy dz equal to, with, so the same integral bounds. Now again, we have the same fluid, rho g, and then again, same case as this one, we're going to have going to define this as h2, but of note, h2 is a function of y right here. And then we have dy dz. So rho and g are constant, so we could put them outside of the integral and then simplify them out, which means we get, so mu 1 is equal to y h1 dy dz is equal to integral with integral this of y h2 dy dz. Now another thing we can also do is we know that this integral dz, nothing here depends on our depth, or sorry, our width, which means we could take the integral on both sides, which means we'll get w0, and which means they'll cancel out. So because they cancel out, L1 h1 dy is equal to integral L2 y h2 dy. Now we need to define what is h1 in function of y right here. So the function h1, so if we look at our integral right here, what we're going to be doing essentially is starting, so if we're looking at the first area 1 right here, we're going to be moving along from 0 all the way up to L1 right here. So what we want is that we want our value of the height to be at this point right here. So when we're at point 0, we want the height to be h minus, well, this height right here. So that means that at the bottom right there, h, maybe I'll use another marker. So at the bottom there, reach the bottom, we know that h1, h minus L2, which means that, sorry, when our height is y is equal to 0, we get h minus L2, which means we're at the start of the hinge. Now, our y is also, h1 here is a function of y, because as we move up to y right here, so let's say that if y was equal to L1 right here, which is our bound of our integral, now we want this total height here to be h minus L1 and L2 here. That means that if we add minus y right here, we get the correct equation. Now I'd recommend you guys taking the time and doing this part by yourselves, because this is what confuses a lot of people. It's very easy to mix up, but what you would do just to double check that this is correct, y right here, if we have y 0, so we're at a height of 0 right here, well, we get h minus L2. H minus L2 means that we have the height, we have this height right here. Now, if y was equal to the top bound of our integral, L2, well, our total height right here would be h minus L2 minus L1, which means we would get this height right here. And so this kind of middle section right here is what we're evaluating in the integral. Now the same logic can be again applied for h2. So h2, again, what we're looking for is h2 is going to be defined by y, but also this height right here. So we know height plays a factor in it, the total height, right there. And then what we'll do will be L2 plus y. So why does this work? Well, again, if we look at our system that we have, we already defined here this y as being positive. So as we're moving along in this integral, when we start and y is equal to 0 right here, what we want is this height right there. So if y is equal to 0, well, we get the height h minus L2. H minus L2, well, that is this height right here. Now, if as y increases and moves towards L2, we get our final value, which is y is equal to L2, which means that H2, the smaller H2, becomes H2 minus L2 plus L2, which means it becomes H. So again, with this integral, we're starting here at 0, and then we're moving our way down here. Now that we have these two defined, we can put them into the general equation right here. So now the general equation becomes the integral 0 to L1 y h minus L2 minus y dy is equal to h minus 2 plus. Now this just becomes some calculus. So this becomes 1/2 hy squared minus 1/2 L2 y squared minus 1/3 y squared. And this is going to be evaluated from 0 to L1. It's going to be equal to 1/2 h y squared to y squared plus 1/3 cubed evaluated L2 0. Well, unfortunately, the last little part of the video cut out, but the idea is still the same. So I was just expanding out this term. Take L1 after the 0 right here all becomes 0, so we just have to replace L2 inside of y here and L1 inside of y right there. We know the values of L1 and L2 right here, so we can just replace it. Just some pen and paper calculations. We can isolate then for h, and we get our final answer right here, which is h is equal to 2.2 meters.